Hello everyone, this is Lecture 7 of ComSci 141, Properties of Regular Languages. In the last video, we discussed finite automata extensions, where we looked at the 2DFA, the Moore machine, Mealy machine, and the equivalence of Moore and Mealy machines. In our finite automata outline, we are currently in the last topic, Properties of Regular Languages, and in today's video, we will discuss decision algorithms for regular languages, closure properties of regular languages, and we will also see something called the product DFA. So to start, for language representations, we usually have two forms. We have the informal version, which is a logical or prose statement about the language strings. So for example, you have the set former notation 0n 1n, where n is greater than or equal to 1. Or you could also have the English description, set of binary strings consisting of some zeros followed by the same number of ones. So this type of representation is informal. On the other hand, formal language representations are precise mathematical definitions. For example, regular expressions and your finite automata are formal language representations. Now, in answering questions about the language, we need to use formal representations. So for example, if we were to answer the question, is language L infinite? We need to use either the finite automata or the regular expression to prove that it is infinite or not. We cannot use the informal versions like English descriptions to prove this to be true. Okay? So we do this for something called a language class, which is simply a set of languages. Well, we have already seen one language class so far, which is the regular languages. So that's what we've been discussing so far. Now, after regular languages, in our second set of topics, we will discuss context-free languages, and then after that, we'll discuss recursively enumerable languages. But these three are called language classes because they're just a set of languages. Okay? And for each language class, they have something called a set of decision algorithms and closure properties. So for today, we will discuss the decision algorithms and closure properties of the regular language class. So what are decision algorithms? These are algorithms that answers the question, does a certain property hold true? Okay, so for closure properties, on the other hand, we say that the language class is closed under an operation if that operation produces an output that's in the same class as the operands. So if that doesn't make sense yet, don't worry. We'll discuss what that means later when we look at closure properties. But for now, let's take a look at decision algorithms first. So what are decision algorithms? They take in as an input a formal representation of the language, so either finite automata or regular expression, and the output of the decision algorithm is yes or no, which answers the question: does a certain property hold true? Okay. So what are these properties? So first, we have the membership property. So it answers the question: is the string W part of the language? Next, we have equivalence. So given two languages, L and M, are they the same? Are they equivalent? And then containment. Is L a subset of language M? And then emptiness. Is the language L empty? Infiniteness. Is L an infinite language? So does it have an infinite number of strings? So those are the decision properties that we'll look at for our regular languages. Okay, so let's start with membership, the membership problem. So we've actually seen this in our discussion of our finite automata, but let's just go through it formally. Okay, so in the membership problem, we decide whether the string W is part of the regular language L. Okay, so is string W a member of L? And for our input, we will take the DFA representation of the language. And for the output, whether accepted or not, ang string. Okay. So for the membership algorithm, um, it's straightforward. So we know that L, the given L, is a regular language. So we know that there exists a finite automaton that accepts the same language by Kleene's theorem. So remember that Kleene's theorem tells us that all regular languages have a finite automaton, and if it's a finite automaton, there is a regular language. It is a regular language, right? So we will choose the DFA representation, which is a formal representation. And what we'll do is we'll simulate the action of the DFA on the sequence of input symbols forming string W. So we will do what we have been doing for string acceptance in our DFA. So we'll just follow the state transitions, and um, we'll see where it leads after we have finished processing all of the input symbols. So after reading all symbols of the input string, if we end up in an accepting state or a final state, then we accept string W. So it's a member of the language. Otherwise, if it's a non-accepting state that we ended up in, then string W is rejected, and that means that it's not a member of the language. Okay, so we've already seen this in the previous videos. So hopefully it's not so much of a problem anymore. Okay, so that's membership algorithm. Let's now go to the next one, which is emptiness problem. So in the emptiness problem, we decide whether the regular language L contains any strings at all. So is it empty or not? Okay, so we will also use the DFA representation of the language, and the output would be whether the language is empty or not empty. Okay, so for the algorithm to find out if it's empty or not, what we'll do is we'll compute the set of states that are reachable from the start state using BFS or DFS traversal. So by traversing using breadth first search or depth first search, we can reach certain states from the start state, and those that are reachable, we'll take a look at those states, and if one of those states is a final state, then the language is not empty, because that means that we could accept at least one string, because a final state is reachable. Okay, so find out the reachable states. If one of them is a final or accepting state, then it's not empty. Okay, so let's see. Given this DFA as an example, is this empty or not? So let's try to see what states are reachable from the start state. So our start state is A. So let me this one. So our start state is A. So this one is reachable, of course. And then we can also reach C. Then from C we can reach E. From A we can also reach B. From C we can reach F. From E we can reach G, and from B we can reach D. So all states are reachable, and of course there are final states that are reachable. So this language is not empty because we can reach some final states. Okay, so yeah. Now let's see for this DFA if it's empty or not. So let's see what are the reachable states. So starting from start state A, which is the start state, we can reach B, and from B we can reach D, but that's it, right? Because D doesn't have any outgoing edges. From A we can also reach C, and we can also reach E, but that's also it, because from F there is no way to reach F starting from the start state. Same with H and G. So is this language empty or not? So from the set of reachable states, we don't actually have any final states. So that means that this language is empty because we cannot accept any string, because no final states are reachable from the start state. Okay, so that is how you determine whether a regular language is empty or not. So you traverse the DFA and find out the reachable states and check if there are any reachable final states. Okay, so that's emptiness. Now let's move on to finiteness or infiniteness. So we have this statement here. Every finite language is regular, but a regular is not. But a regular language is not necessarily finite. So what does this mean? If if it's a finite language, that means that you could actually enumerate everything. Then that is automatically a regular language, because if we can enumerate everything, then we could just write the corresponding regular expression, which is, for example, if the language contains the following strings: 0 0, 0 1, 1 1, and 1. So if these are the four strings in the regular language, we could just write an equivalent regular expression with just the union of all strings, right? Because we could enumerate them since it's finite. So this is already a valid regular expression, so therefore it's regular. However, a regular language is not necessarily finite, because there could be infinite languages regular, okay, as we'll see in the later examples. Okay, so the infiniteness problem decides whether the given regular language L is infinite or not. Okay, so there are two ways that we could solve this problem. So there are two solutions. First is by finding cycles in the DFA, and we can also look at the regular expression to check if it's infinite or not. So let's take a look at how to find cycles in the DFA first, in order for us to see if it's an infinite language or not. So what we'll do is we'll try to find cycles between the start state and the final state. Okay, and we'll do this because if you have a cycle or a loop within your DFA, you can take that infinitely, right? So if you take that infinitely, then it will produce infinite strings as well. Okay, so in finding the cycles, we have to do some cleaning up of the DFA first, because it might not be simplified. So we need to eliminate some unnecessary states. So first, we will eliminate unreachable states from the start state. So just like what we did earlier in the emptiness problem, we will traverse starting from the start state and take note of those that are reachable na states. If they are not reachable, then we will remove them, because anyway, we cannot reach them from the start state, so they're really useless. Okay, and the second step is we'll also eliminate states that don't reach a final state. So if a state cannot reach a final state, then there's also it's also not a factor in finding cycles, because it will not lead to the final state anyway. And our goal is to find cycles from the start state to the final state, right? So if you don't reach a final state, you'll also be eliminated. Okay? And in the remaining graph, after we've removed the unnecessary states, if it has any cycles, then we can conclude that the language L is infinite, because we could take that cycle infinitely to produce infinite strings. Okay? So let's see an example. Um, does this have a does this DFA have an infinite language? So first, let's eliminate unreachable states. But all states are reachable from the start state, because from A, of course, you can reach A. From A, you can go to B. And from B, you can go to C, right? So all states are reachable. Now, the second step is to remove the states that cannot reach a final state. Now, A can reach a final state because it's a final state itself. B is also a final state, so we cannot remove this. But C cannot go to your final state, because C can only go to C, right? So we can remove this one. We can cross this out of our DFA, and this will now be our remaining DFA here. Okay. So only this one, because we have already removed the state C. But in our remaining DFA, there is still a cycle. So for example, this self loop is a cycle, and this one is also a cycle. So since there is a cycle in the remaining graph, we can say that the language of this DFA is infinite. Okay, so that's it. How about for this DFA? So first, again, we need to remove the states that are unreachable. So we can only reach states A, B, D, C, and E. So we cannot reach states F, G, or H from the start state. So we'll need to remove them. Okay, so we'll remove them. And then after that, we will also remove states that cannot reach a final state. But all of the states that remain cannot reach a final state since we have removed all the final states, right? So they also cannot reach a final state, so we'll also remove them. C, D, and E. So what we don't have anything left anymore. So the remaining graph is empty, and because it's empty, obviously there are no cycles. So because the remaining graph has no cycles, we can say that the language of the DFA is finite. In fact, it's even empty. So because it's empty, that's also finite because there's nothing there that's countable. It's zero. Okay, so that is how you um, determine if a language given the DFA is infinite or not. So if you find the cycles after simplifying the DFA. Okay. Now, the second way to check if it's infinite or not is by looking at the regular expression. So how do you determine if a regular language is infinite just by looking at its regular expression? So we have three main operators or operations for regular expressions. We have union, concatenation, and closure. Which among those three do you think makes a language infinite? So it's the closure or the Kleene closure operation. So if a regular expression has a closure or the star, then the language is infinite. Okay, because closure or the star um, means that you could take zero or more copies of that symbol or string that you are closing. So you can take that as many times as you want, so that therefore the language is infinite. But this is not always the case, okay? There are some exceptions because, for example, if you have 0, epsilon star 1, so there is a closure here, but epsilon star is only epsilon, right? Because no matter how many times you take an empty string, it's still empty. And then if you have 0 star null, you concatenate the 0 star, which is infinite, with null, which is the annihilator for concatenation, then this will also produce null, right? Remember? Because you cannot concatenate uh, a language with null. So if you concatenate the two, it will produce null language as well. Okay? So first, we need to also simplify the regular expressions to remove those expressions that could be tricky, right? So it might be misleading to say that because there is a Kleene closure in that expression, automatically infinite na siya. So first, what we'll need to do is we'll find sub-expressions that are equivalent to null. So for example, E plus F, so the union of E and F is null if both E and F are null. Okay, so that would be if it's null union null, then that's just null. You can simplify it that way. Okay. Um, Next, you have EF, or the concatenation of E and F is null if either E or F is null. So if it's, for example, E null or null F, then since it's concatenation and null is the annihilator for concatenation, that is just equal to null if either E or F is null. Okay. Epsilon star, sorry, E star is never null because at the very least it could have epsilon. Okay, so it's just this two that we can simplify. And then next we will eliminate the sub-expressions that are equivalent to null. So we will replace it E plus F by F when E is null. So we'll simplify that one, and we'll also replace uh, E star by epsilon when E is null. So if you have something like null star, then just replace that with epsilon, because if you take the closure of something, you have at least epsilon, right? So we'll eliminate the null sub-expressions, and then we will also find the sub-expressions that are equivalent to epsilon and simplify them. So E plus F is equal to epsilon if both of them are epsilon. So that would be epsilon plus epsilon is just epsilon. So union of epsilon and epsilon is just epsilon. And then EF is just epsilon if both E and F are epsilon. So if you concatenate two epsilons, that is just epsilon as well. Okay, so we'll just also simplify that one. And uh, epsilon star is also just epsilon. Okay, so we'll simplify all sub-expressions that are just one epsilon worth. Okay, and then after you have simplified everything, then we will check if the language of the regular expression is infinite if there is a sub-expression E star, so there's a closure where the expression is not equivalent to epsilon. Okay, so let's take a look at an example. So given this regular expression, let's try to simplify this and check if it's a infinite language or not. So first, find the uh, expressions that are equivalent to null, and we have one here. So one null is just equivalent to null because you cannot concatenate the two. So annihilator is null for concatenation, so it's equal to null. So we can rewrite this as 0 plus null quantity star plus 1 null star. Okay, so we have simplified this one. Next, we'll remove all the not unnecessary null characters or symbols, and we can find that one here. So 0 union null, so you're not really adding anything new because it's union null, so it's just equivalent to 0, right? And then we also have null star, so null star is just equivalent to epsilon, right? So we simplify that here to so this will become 0 0 plus null is equal to 0, so this becomes 0 star here, and then um, null star is equal to epsilon, so that's why this one became 1 epsilon. Okay, and then the third step is find unnecessary epsilons, so we can simplify them, and we find one here, so 1 epsilon, so this one will become just 1 plainly. Okay, so we can simplify this to become 0 star plus 1. Okay, so that is the final simplified regular expression. So we now will decide, is this infinite or not? So it is infinite because of 0 star here. So there is a closure and it's not epsilon. So it's infinite because there is a closure. Okay, so that is how you determine if a given language is infinite or not given its regular expression. So simplify it first by removing the nulls and the epsilons. So we'll write their equivalent expressions, and then the resulting regular expression, we examine it if it has a closure, and if it has, then it is infinite. Okay, so that is the infiniteness problem. Um, let's see more examples. Okay, for this one. Which of the following regular expressions represent an infinite regular language? So how about this one? Um, so we can simplify this. Null star becomes just epsilon, right? So epsilon plus 0, this just becomes just 0, right? So this is 0, 1 plus 0, 1. So is this finite or infinite? So it is finite because there is no closure. So we have eliminated the deceiving closure here, null star, which is just epsilon. Okay. How about this one? Uh, we don't need to simplify this one. It's already simplified. And this is infinite because of 1 star and even the 0 star here. Okay. Finally, let's look at this one. So let's try to simplify it. Um, 1, 0 union null. This just becomes 1, 0, right? Because of union with null is the item itself. But 1, 0 will have a star. Okay, so the resulting regular expression is 0, 0 plus 1, 1, and then concatenate that with 1, 0 quantity star. So the final regular expression still has a closure. So this is also infinite. Okay, so that's it for this one. Let's now go to the equivalence problem. So given two regular languages, L and M, we decide whether L is equal to M. So are they equivalent languages? Okay. What we'll use for the proof is the um, DFA representations of the two languages, and the output is of course whether they are equivalent or not. Now for this problem, what we'll do is we'll create or construct something called the product DFA. So the product DFA is you create this out of two DFAs. So given the DFAs of L and M, we'll create a product DFA. And essentially what this does is it allows us to run both DFAs in parallel. Okay, so we'll combine the two DFAs into one product DFA. Um, okay, so how do we construct this product DFA? So let's say that the states of the DFA in L, or the first DFA, is denoted by Q, and the states in DFA of M are denoted by R. The states in the product DFA are of the form QR, wherein Q is part of the set of states in the first DFA, and R is part of the set of states in the second DFA. Okay, so um, and for the start state, we will use the state Q0, R0, wherein Q0 and R0 are the start states in the first and the second DFA respectively. Okay. And then for the transition, what we'll do is um, the the delta of QR, the state QR on A is just the state delta of Q on A and then delta of R on A. So the destination of the transition Q on A in the first DFA, and then the destination of the transition R on A in the second DFA, and then we'll take those two states, and that will be the state name of the destination of this transition. Okay, so if that doesn't make sense, we have a illustration here to help you understand this better. So if in the first DFA we have this transition Q to P on A, and then in the second DFA we have this transition R to S on A, in the product DFA we will have states like QR. So the Q is from the first DFA, the R is from the second DFA. So you have QR, and then we also have state PS. So P is from DFA 1, S is from DFA 2. So what would be the where would state QR transition to on input symbol A? So Q on A goes to P and R on S goes to R on A goes to S. So that would be the state PS here. So that's why the product DFA will go to PS on A. Okay, so that is how you create the product DFA transitions. Okay, so given this two DFAs, let's now try to create the corresponding product DFA. Okay, so we will have 4 states here. That would be the states um, A, C, then we have A, D, then we have B, C, and B, D. Okay, so first of all, where did we get these states? So for each state in the first DFA, we will combine them with the states in the second DFA. So AC, AD, and then we'll also do the same for B. So BC, BD. Okay, now how about the start state? So the start state would be the start states of the two DFA. So that would be AC. So our start state is in AC. Okay, so this is our start. Okay, now for the transitions, AC on a 0. So where will that go to? So A on 0 goes to A, C on 0 goes to D. So that is AD. So this will go to AD on a 0. Okay. How about on a 1? AC on a 1. So A on a 1 goes to B. C on a 1 goes to C. So that is BC. So AC on 1 goes to BC. Okay. Now how about for AD? Let's try it with 0. So AD on 0 is goes to A, and then D on 0 goes to D as well. So that is still in AD. Okay, so we have a self loop here on 0. But on 1, AD will go to A will go to B, and then D will go to C on a 1. So that is BC. Okay, so we will cross here on a 1 to BC. Now, how about for BC? BC on 0, where will that go to? So B on 0 goes to A. So B on 0 is to A, and then C on 0 goes to D. So that is AD. So BC on 0 will go to AD. Okay, and then on 1, B goes to A, and then C goes to C itself. So that would be AC on 1. So we'll go to AC on 1. Okay, and then lastly, we will process BD. So B on 0 goes to A, and then D on 0 goes to uh, so again, B on 0 goes to A, and then D on 0 goes to D. So that is AD, right? So BD on 0 goes to AD. And then on 1, B goes to A on 1, and then D goes to C on 1. So that's AC. So it's all the way up here. So we need to loop this all the way here. On a 1. Okay, so this is now our product DFA for these two DFAs. Okay. Um, okay. Now, so we can see that they are the same here, right? But what about the final states? Okay. So for the final states in this one, um, so for the final states of the equivalence na problem, we will make the states QR such that exactly one of Q and R is a final state of its own DFA. So going back here, those states would be ang B, example A, C. Why is this a final state, AC? Because only one of them is a final state. So C is a final state, but A is not. And then you also have BD as a final state because B is a final state, D is not. So dapat only one of them is a final state in their original DFAs. So that is why we have AC and BD as the final states in our equivalence. Okay, so states such that only one of the states Q and R is a final state in its own DFA. So the product DFA actually accepts the string W if and only if W is in exactly one of L and M. So only if it's in L or in M but not in both. Okay? So dapat either in L or in M lang siya. Now why are we doing this? Remember that we are trying to prove that L is equal to M, right? That they are equivalent. And for L is to be equal to M, we must show that L is a subset of M and M is a subset of L, right? From your early math classes before, so set theory. So L will only be equal to M if they are one and the same set, right? So like total overlap. So there are no items that are extra. So for example, if there are some items in L that are not part of M or some items in M that are not part of L, then they're not equal anymore, right? Or if M is a subset of L or M is a subset of or L is a subset of M. So whichever way is bigger, if one of them is a subset of another, then they cannot be equal also. And then if they are totally disjoint, then that means that obviously they are not equal because they're two totally different sets. So the only way that they will be equal is if they totally uh, intersect with each other. So total overlap. Okay, so they must be a subset of each other. So the language of the product DFA that we are creating for equivalence algorithm is the set of strings W such that W is in L but W is not in M, or W is in M but W is not in L. So either it's in L or it's in M but not in both. Okay, so um, why are we doing this? It's because if the product DFA's language is not empty, then that means that there is a string W that is not common to L and M, because this string W is in L but not in M, or in M but not in L. So there is an uncommon string if the product DFA's language is not empty. And if there is an uncommon string, obviously they will not be equivalent anymore because there is a difference. Okay? So we can say that the two languages L and M are equal if and only if the product DFA that we created has an empty language. Okay, so if it has an empty language, that means that there are no strings that are in L but not in M, or in M but not in L. So we can conclude that all strings in L are in M as well, and vice versa. Okay, so that is how we'll do it. So in our example DFA earlier, is the language empty or not? Okay, so remember the emptiness algorithm. So we'll try to reach all of the possible reachable states from the start state. But from the start state itself, we can already reach a final state AC because it's the start state and also a final state. Okay, so the accepting state AC is already reachable from the start state AC because it is the start state itself. So because a final state is reachable from the start state, we say that the language of the product DFA is not empty. And because it's not empty, that means that the two languages are not equivalent. Okay? So, yeah, that's how you check if two languages are equivalent using product DFA. Okay, let's now go to the next decision problem, which is the containment problem. So given two regular languages, L and M, decide whether L is a subset of M. Okay, so is M a bigger language and L else strings are all part of M as well. So subset ba siya? And we'll also use the DFA representations of L and M in the containment problem, and we'll output whether it's a subset or not. Okay. Um, to check whether L is a subset of M, we will also construct the product DFA of the two DFAs for L and M. But this time, the final states will be different. Okay. The final states would be states QR such that Q is a final state and R is not. So earlier, we said that as long as one of them is a final state and the other one is not, it's fine. That was in equivalence. But here in containment, the final state must be from the first um, DFA only and not the second. Okay? So yeah, those are the final states. And basically what the product DFA accepts are the set of strings W that are in L but not in M. Okay, so meaning it's a string that's accepted by the first DFA but is not accepted by the second DFA. So why are we doing this? Now recall that to show that L is a subset of M, all for all strings W that are part of L, they must also be a part of M, right? For it to be a subset. Okay? But for the product DFA, what we are doing, because we want the strings that are in L but not in M, right? So we are actually uh, trying to find out the opposite language of this one. So all the strings that are in L but not in M. Okay? Are there any such strings? So if there are strings that are in L but not in M, that means that L is not a subset of M. Okay? Because there are some strings in L that are not in M. So L is a subset of M if and only if the product DFA's language is empty. Okay? So that's what we'll do also. So going back to this example, if we check our product DFA again, this time our final state would be what? So the final state for containment would be that would be the state B D, right? Why is that? Because B is a final state in the first DFA and D is not a final state in the second DFA. Okay, so all states such that the first component is a final state and the second component is not a final state, those will be final states in this one. So um, this is the product DFA for containment. So is the language of the product DFA empty? To check, what are the reachable states from AC? So from AC, we can reach AD, we can also reach BC, but we can actually not reach BD. BD is unreachable. So if we remove this one, then we cannot reach any final states. So because there are no final states that are reachable, this is actually empty. Okay. So the product DFA's final state is unreachable from the start state. So the language is empty. Okay. So because the product DFA's language is empty, then we can say that L is a subset of M. Okay. Yeah. Okay, so that's it for your decision algorithms. Let's now look at the second part of the properties of regular languages, which are the closure properties. Okay, so what are closure properties? So a language class is closed under an operation if applying the operation produces another language in the same class. Okay, so what does this mean? So given two languages A and B, which are part of the language class, let's say the regular languages, if we apply the operation to A and B and it produces C, and C is also part of the regular languages, and always, then we say that the regular languages are closed under this operation. Okay, so to make it clearer, let's see some examples. For example, integers are closed under addition, subtraction, and multiplication, because if you add two integers, it will still be an integer. If you subtract two integers uh, from each other, it will still be an integer, ang result. And if you multiply two integers, the result will still be an integer, right? However, integers are not closed under division, because if you divide two integers, the result could be a float, right? So, example, 5 divided by 2 is 2.5. So, that's not an integer anymore. So, because the result is not always the same as the operands, so it's not closed under that operation. Okay? Now, are negative integers closed under addition? Well, yes, because if you add two negative numbers, so minus 5 plus minus 3, that would still be a negative number always, right? Now, how about under subtraction? Is it closed, ang negative integers? Well, it's not. Because, for example, if you take negative 3 minus negative 5, so what will happen is it will become minus 3 plus 5, and that will become positive 2. So um, the result is not a negative integer anymore. So negative integers are not closed under subtraction. How about under multiplication? Are negative integers closed under multiplication? It's also not closed under multiplication because, for example, if you take negative 5 times negative 3, that would be positive 15. So it's not a negative number. Okay, so it's not closed under multiplication. Okay, so hopefully that makes you understand the concept of closure for operations better. So for our closure properties of regular languages, we are given two regular languages, L and M. And if the operation is applied to L and M and it produces N, and N is always a regular language, then the regular languages are closed under that operation. Okay? So what are these operations that are under closure properties? So the regular languages are closed under the following operations: union, concatenation, Kleene closure, intersection, difference, complementation, reversal, and homomorphism. So we'll take a look at each one briefly, starting with union. So for union, if the two given languages L and M are regular languages, then the union of L and M is also regular. Okay, and the proof of that, for the proof, we will use their regular expressions. So because L and M are given to be regular languages, then they will have a regular expression associated with them. So let's call that R and S respectively. So to get the union of L and M, then we'll just get the union of R and S as a regular expression. And this is already a valid regular expression by definition, because union is a basic operation for regular expression. So because this is a valid regular expression, then this language is also regular because it has a regular expression. So that's it. So we have proven that union of L and M is also regular because there is a regular expression for it. So with the same idea or concept, we can prove that concatenation is also part of the closure for regular languages. So if L and M are regular languages, so is the concatenation LM, and we'll also use the regular expressions for the proof. So um, if R and S are their regular expressions, then we can just use the R concatenated with S as a regular expression um, for the language LM. And this is a valid regular expression by definition because concatenation is a basic operation for regular expressions. Okay, and we'll also use the same argument for Kleene closure. So we'll call this Kleene closure to differentiate it from the closure property, so that it's not confusing. So if L is a regular language, so is L star, the closure of L. So we'll also use the regular expression R, and we'll just take R star, which is a valid regular expression by definition. Okay, so for union, concatenation, and closure, the language produced by applying these operations has a corresponding regular expression by definition, because those are the three basic operations for regular expressions, right? So we can say that the resulting language is also regular because it has a regular expression. Okay, so those are the first three operations. Let's now look at the next one, which is intersection. So if the two given languages, L and M, are regular languages, then their intersection, L intersection M, is also a regular language. And for the proof, we will use their DFAs. So the DFA of A and B, we'll call that we'll call the DFA of L and M A and B respectively. And what we'll do is we'll construct the product DFA of A and B. So we'll go back to the concept of product DFAs again. So this time, the final states for the product DFA would be the states A, B, such that both A and B are final states in their original DFA. So because this is intersection, we want the states that are accepting in the first DFA and also accepting in the second DFA to be the final states of our product DFA. Okay, so that means that it's accepted in both DFAs. So intersection siya. Okay, so the product DFA accepts the string W if and only if the string is accepted by both A and B. So this product DFA represents the intersection of the two DFAs, and the language is L intersection M. Okay, so going back to this example, what do you think would be the um, final state for this product DFA? So for the final state, that would be B, C, because those are the two that's the only state wherein both states are final states in their original DFA. So BC. Okay. So BC is the final state here. Okay. So you'll notice that for the product DFA, for the construction, we have the same construction of the product DFA, but the final state depends on its usage. So whether we use it for intersection or equivalence or for containment, um, the final states depend on our purpose. Okay, so that is how you create the product DFA for the intersection. And because we have a DFA for the intersection of the two languages, then obviously it's also a regular language. Okay. Okay, next, let's look at the difference operation. If L and M are regular languages, so is the difference of L minus M. So L minus M is also a regular language. So remember that L minus M is just the set of strings W such that W is part of L but not in M. Okay, so all the strings in L that are not in M. So for the proof, we will also use the DFA of the two languages. So we'll call that A and B. And we'll also construct the product DFA. But this time, for the difference, the final states would be states A, B such that A is a final state, but B is not. So since it's a difference, so L minus M, it's accepted in L but not in M. So we'll only take those with final states in the first DFA but not in the second DFA. Okay, so the product DFA accepts the string if and only if it's accepted by A but not by B. So it represents A minus B and its language is L minus M. So the language L minus M has a representative product DFA, so that means that it's regular as well. So going back to our example, what would be the final state of this one? That would be B, D for difference, right? Because B is a final state in the first DFA and D is a non-final state in the second DFA. So that would be the final state, BD. Okay? Now, is the language of this product DFA empty? So we've actually seen this one earlier, and we have seen that it is indeed empty because the only reachable states are AC, BC, and AD. BD is actually unreachable. So, and since it's the only final state, then the language of this product DFA is empty. Okay, so it's unreachable. So L minus M is actually empty. And the reason for that is if we try to describe the languages by the two DFA, we'll actually see that the first DFA gives you binary strings that end with an odd number of ones. So going back here, so as long as you have an odd number of 1 as the ending, so for example, if you end in 1, that's odd, so you will be accepted. Or if you end in 1, 1, 1, so that's 3 ones, that's still odd, you still end up in B. Okay, but if you have an even number of ones, so 1, 1 for example, then it's not accepted. Or if you end in zeros, it's also not accepted. So the first DFA is a set of binary strings that end with an odd number of ones. For the second DFA, this would be a set of binary strings that end in at least 1 plus epsilon. So it accepts epsilon because at the start itself, it's already accepting, so that's epsilon. And then it also accepts strings with at least that end in at least 1 1. So ends in at least isa ka 1. Okay? So for example, you end in 1, 1, 1, 1, 1. So if it's 0, if it ends in 0, it's not accepted. But if you end in 1 again, it's accepted. Okay? But you'll notice that the second language is actually a superset of this language because ending in at least 1, 1 will be will consume or will be a superset of that binary strings that end with an odd number of ones, because you could have an odd number here or even number, doesn't matter, it's just at least one, right? So because the language of the first DFA is a subset of the second language, their difference is null because it's a subset. Okay, so that is why for our product DFA it was null ang language niya earlier. Okay, so that's it for difference. Now for the next operation, we have complementation. For complementation, the complement of a language L with respect to an alphabet sigma, such that L is a subset of sigma star, is sigma star minus L. So all of the strings that are not in L that are in sigma star. So complement basically. So if you have the um, if you have a set, for example, that would look like this. Guess we can remove this already. So if it's a set, if this is the universal set, sigma star. Sigma star is your universal set, and this is your language. The complement is everything that's outside of the language, but are part of sigma star. Okay, so that's the complement. Um, and if L is a regular language, so is its complement. So sigma star minus L is also regular, and the proof is well, sigma star is automatically regular because this is just Kleene closure, right? And L is regular also because it's given to be regular. So sigma star minus L is also regular because this is just a difference of two regular languages. And we have already seen earlier that the regular languages are closed under difference. So we can assume that complementation is also regular because of this one. Okay? So we just piggyback on the proof of difference because we can reduce complementation to difference. Okay, so that's it. And then let's move on to our next operation, which is reversal. Now for the reversal, um, given a language L, the reversal of this language is the set of strings that are reversed for each string in L, basically. So, for example, if your language is 0, 0, 1, and 1, 0, 0, the reversals of these strings would be 0, 1, 0, and 0, 0, 1. Okay, so those are the strings in the reversal of the language. And if L is a regular language, so is its reversal L sub LR. Okay, and the proof is can be seen using its regular expression. So if we'll use the regular expression for L, we'll call that E, and we'll provide a regular expression for the reversal. And to do that, what we'll do is follow this follow these steps. So if the expression is just a symbol or um, epsilon or null, then the reversal of that symbol, epsilon or null, is still epsilon. So we have um, x reversed is still x. We have epsilon reversed is still epsilon, and null reversed is still null, right? So we don't really reverse it because it's just a single symbol itself. Now, if we use union, so union of f and g, for example, the reversal of this expression would be the individual reversals of the two expressions. So reversal of f, union, reversal of g. Okay? So that's for union. For concatenation, E, F, G, what we'll do is to reverse this one, we will reverse the order. So instead of FG, we will take G first and take its reversal. So that would be G reversed, and then we'll take the reversal of F. So notice that we have also interchanged the order of F and G. So it's now G and F, and take their individual reversals. And finally, for the closure, if it's, for example, F star, the reversal of this expression would just be take the reversal of F first, and then take the star. Okay, so those are the rules for reversing a regular expression. So let's see this in an example. For our expression 0, 1 star plus 1, 0 star. So this represents the set of binary strings where the first digit never appears again. So either it starts with 0 followed by 1s, so that's 0, 1 star, or it starts with 1 followed by zeros. Okay, so for this one, how will we reverse this regular expression? So let's start with this one. So the whole thing will be reversed, right? So we have 0, 1 star plus 1, 0 star, quantity reversed. So the first thing that will reverse here is the union, right? Because it's um, the one with a bigger, or the one with so we can think of this as expression union expression reversed, right? So to do that, then we'll just have 0, 1 star reversed plus 1, 0 star reversed. So FR plus GR, right? So we'll reverse this expression right here, and then we'll also reverse this expression right here. Okay, so the next thing that we'll look at would be the reversal of your um, concatenation, which is we have two here. So we have 0 and 1 star. This is a concatenation, and we'll reverse that. And then 1, 0 star. That's also a concatenation if we reverse that. So for the reversal of this 0, 1 star, that would be 1 star, and then take the reversal. And then 0, take the reversal. And then you take the union with, for this expression, we'll take 0 star reversed, and then 1 reversed. Okay, and then next we will simplify also ang closure expressions. So if it's a reversal of a closure, then you just take the reversal first. So this becomes 1 reversed and then closure 0R. And then for this one, that would be 0 reversed, take the closure, then 1 reversed, right? So we have now simplified it. And then let's also simplify this too. So 0 reversed and 1 reversed is just 0 and 1 respectively, right? And then since we have a reverse here as well, na 0 and 1, we'll also simplify that to 1 and 0 respectively. So we'll now have 1 star 0 and 0 star 1 with the reunion. Okay, and that is now your final reversed regular expression. Okay, so since we have produced a regular expression for the given regular expression for the reversal, then the reversal is also a regular language. Okay, so if we erase all of this, we were given 0, 0, 1 star plus 1, 0 star, and this was the set of binary strings where the first digit never appeared again. For the reversal, it was 1 star 0 plus 0 star 1, or the binary strings where the last digit doesn't appear elsewhere. So if you ended in 0, it did not appear in the prefix, and if you ended in 1, it also did not appear in the prefix. Unlike here, wherein if you start in 0, it will not appear in the suffix. If you start in 1, it will not appear in the suffix. Okay, so we reversed all of the strings in that language. Okay, now the next and the last operation is homomorphism. So the homomorphism on alphabet sigma is a function that gives a string for each symbol in sigma. So you can think of this as like a translation function or a mapping function that maps a symbol to another symbol. And you can even extend this to strings. So if you apply the homomorphism for a set of strings, a sub 1, a sub 2, up to a sub n, ang i-input symbols, then just take the individual homomorphisms of the individual symbols and take their concatenation. Okay? So let's say, for example, our homomorphism for 0 and 1 is, so h of 0 is AB and h of 1 is epsilon. So that means that if we see an input symbol 0, we'll replace it with the string AB, and if we see 1, we'll replace it with epsilon. So for this input string, 0, 1, 0, 1, 0, that would all of the zeros would be replaced by ABs here, and all of the ones would be replaced by epsilon. So if we simplify this one, the homomorphism of 0, 1, 0, 1, 0 given this function here is AB, AB, AB. Okay, so homomorphism is just mapping basically. So if L is a regular language and H is a homomorphism on its alphabet, then the homomorphism on the language H of L, wherein it's a set of strings HW, it's also a regular language. Okay, and the idea for the proof is shown also by using a regular expression. So if E is the regular expression for the given language L, we'll apply the homomorphism function to each symbol in the regular expression, and the language of the resulting regular expression is H of L. Okay, so we'll just map the homomorphism to the regular expression. So for this example, given this uh, homomorphism function, h0 is equal to AB, h1 is equal to epsilon, let's try to um, see the resulting language if we apply the homomorphism on L, which is 0, 1 star plus 1, 0 star. So we'll just replace the zeros and ones with AB and epsilon respectively. So 0 here will become AB, and 1 here will become epsilon. So that will become AB epsilon star, epsilon AB quantity star. So we can simplify this by epsilon star is just epsilon. So this will become just AB, right? And then AB star concatenated with epsilon is just AB quantity star as well. So this is the resulting regular expression, but even AB here is already part of AB quantity star. So we can simplify this further to be just AB quantity star. Okay, so we have created the corresponding regular expression for the homomorphism. And since we have a regular expression, then the homomorphism is also a regular language. Okay, so that is how you apply homomorphism to the regular language. And that's it for this video. So to review, we have discussed a lot of things in this video. So we discussed the product DFA, which essentially runs two DFAs in parallel. Okay, so if the states Q are for DFA1 and states R are for DFA2, then the product DFA has states of the form QR, right? So states from from DFA1 and DFA2. Start state would be at Q0, R0, which is the respective starting states of the two DFAs. And then for the transition, just follow this equation. So QR on A will go to delta of QA and delta of RA as the state. Okay, and the final states depends on the purpose. So if it's equivalence or containment or intersection, so it depends on what your use of the product DFA is. So we discussed several decision algorithms for regular languages as well, starting with membership. So just simulate it through the DFA. So emptiness, check if any final states are reachable. Then for infiniteness, once you simplify the DFA, check if there are cycles. And you can also do this for the regular expression. So once you simplify the regular expression, check if there is a closure. For equivalence, we constructed the product DFA and check if the resulting language is empty. And the same thing for containment, we also use product DFA. And then we also discussed some closure properties for regular languages, specifically for the operations union, concatenation, and Kleene closure, all of which use the regular expressions as their proof because they are the basic operations for regular expressions. And then for intersection, we use the product DFA, wherein the final states are supposed to be states that are accepting states in both DFAs. Then for difference, product DFA's final states are those that are accepted in the first DFA but not in the second. Then for complementation, we just piggyback on the proof of difference because we can just express complementation as a difference. And then we also discussed reversal using the regular expression. So we just followed the steps to reverse a regular expression. So we produce a equivalent regular expression for the reversal. And we also did the same for homomorphism. So we just apply the homomorphism function, or so we map the symbols, and then the resulting regular expression for the map symbols is also a valid regular expression. So it's also a regular language. Okay, so that's it for this video. For the next topic, that would be the last lecture before we have our first long exam. So that would be next week. Uh, no, the next topic would be next week. Our long exam would be 2 weeks from now. Okay, so our next topic would be pumping lemma for regular languages, and we'll also discuss how to minimize a DFA. And that's it for this video. And yeah, I will see you next time.